I'm reminded that it's 45 years since Buzz Aldrin was the second man on the moon, and everybody in interviews with him says, what's it like to be second? And he gets really pissed off with it. So somebody said to him, what were you afraid of going to the moon and walking on the moon? He said, nothing, because someone else had done it already. Now today I'm going to show you what has been done already in this field in terms of membrane delivery, but also in public-private partnership with the partnership that's the Compact programme, which is a European grant that we're part of as well. So I'm going to move through this pretty quickly because I've got 19 and a half minutes. So I'm going to show you why we need to improve delivery of macromolecule drugs, especially oligos, which is my area of expertise. How do we measure improved delivery? Because it's all very well saying we've done it, but if it's going to cost you 20 times as much as it did before and you get a twofold improvement, you have not contributed to this problem. You just added to it, okay? I'm going to show you what we've done at GSK. I'm going to show you why we had to phone a friend. And then finally, I'm going to set, as requested, some targets. So let's think about macromolecule delivery. If you give an oligo, where does it go? This is a mouse QWA. The oligo was given into the skin at the back of the neck here. And every single oligo of any chemistry will end up in the kidney and the liver and the spleen and the bone marrow. And that's the reticular endothelial system. That's the garbage trucks of the body. That's where all particulates end up. So if you're trying to deliver there, then you're in clover. And a lot of companies out there will tell you that's the way to go. If you want to go to the kidney cortex, the liver, the spleen or the bone marrow, then you don't have to do any additional distribution. A lot of people will tell you if you change the chemistry, and this is a 2-O-methyl oligo, the backbone's been modified to make it more stable. If you change the chemistry, it's different, but it's not. So this is a phosphorothioate oligo, that's a presensor molecule. This is an aptamer, which is an RNA antibody. This is a locked nucleic acid, RNAs. These are spiegelmers, which are mirror image aptamers, really fancy, but exactly the same distribution. And then finally, the peptide morpholino oligos with self-penetrating peptides, the ultimate in non-charged oligo with a peptide, again, ends up in the liver and kidney. You can't get away from that, which is great until your target's in the muscle, or the lymphocytes, or the brain, because frankly, you ain't going to get anything in the brain with this kind of system. So we're going to have to work how we do that. That's the first challenge, and that's big stuff. Let's get to the cell now, because again, I'm teaching you guys to suck eggs. Let's see where the target, because what I've seen, the pictures of the cells today have been a nice double membrane, and that's it. It's just a big sphere of cytoplasm. It's not, because within there's lots of different compartments as well. And it's great, because if we look where our targets are, if you're really lucky, your target's on the cell surface. Easy to get to, you don't have to cross any membranes to get there. If in vitro, in vivo there's some blood cell membranes and blood vessel membranes. If you're lucky, you might have a target in the endosome, where a lot of the stuff goes automatically. Now, I work with a guy in Cardiff, Arwin Jones, who will swear and beat up anybody who says this is inside the cell, because the endosomal content is still outside the cell. It's like landing in Spain, but being the wrong side of customs. You're still outside the country, even though you're inside Spain. Okay, so it is outside the cell, and we've got to be able to get across that membrane and into the cell to do it. Finally, excuse me, I clicked on too far. Finally, we might have nuclear or cytoplasmic targets. Now, there are easy ways of doing this in vitro to get to our targets. We just wrap it up in lipofectamine or a lipid, bang it on the cell, burst open that membrane, and we get our drug inside. And that's very easily done, and in vitro works really reproducibly. And already Doug's getting angsty. There are ways of getting via the clathrin-mediated uptake, the independent uptake via the endosome. It's great, we get a lot in there. If we put it into a nanoparticle, it gets into the cell, but then it goes straight down to our friend, the late endosome and the lysosome, and fries your drug. And very little gets out of that system. Believe what you like, but at the end of the day, about 0.01% of your drug that started here ends up in the cytoplasm by this route. The third route, the way that a lot of people are looking at now, is via the receptor-mediated uptake, via the caveolin pathway that avoids the endosomal acid bath. It's using cell surface receptors to target that uptake process and to sort your drug into the compartment where you can get it into the cytoplasm and act. And the trick now is to find out what those cell surface receptors are that are trafficking our drug in there. And I'm not talking about small molecule transporters here. I'm talking about large proteins that are recycling through the cell. Okay, can we measure improved delivery? GSK is a business. We set our group up 4 years ago, and we were told if we didn't deliver, and we showed delivery, we'd be over. And we have survived for 4 years, so we've done something. So this is how we measure it. It's an equation. It's got to be an equation. These are the things we'd like to have. We want to increase our target tissue concentration. We want to increase productive uptake, increase our uptake into the right part of the cell, and we want to increase the desired PD. If we can get any of those working, we've got a tick in our box. The trade-off is, what we don't want to do is increase off-target tissue, as in it goes to the wrong place, or increase non-productive uptake, it all ends up in the lysosome, or we get off-target PD or toxicology. And that's the trade-off there. Now, if we increase the top line, it's good. If we maintain or decrease the bottom line, that's good. If we increase the bottom line, that's not good. So it's a simple balancing equation. What we end up with is a real careful control of the cost of goods. Because if we get a twofold increase in the top line, but it costs us 20 times more, we haven't sorted anything out. We've just made it more expensive. But what this means, especially for oligos, is that we can decrease our effective dose, because oligonucleotides in the clinic are bang up against their safety levels. Okay? This is why most clinical oligos are for rare diseases where there is no other cure, because people are prepared to take that risk-benefit equation. You cannot get oligos at the moment into diseases where there are other cures because there are side effects. So if we can drive down the dose because we can get better targeting, we reduce the cost of goods, we make it cheaper to work, and we then get a better dose so we get better safety. So how have we gone about that? This is our options for targeted delivery. And again, I'll try and keep an eye on Doug, but the first thing is picking the chemistry. We've been doing this for 30, 40, 50 years, where you know what you want to get into the cell. You make sure you screen thousands of compounds until you find ones that go in there. Now recently, maybe 10 years, we said, let's think about the uptake transporters and work out what's going on there, and then we can start modeling it. Now this is a picture of the brain. This is a PGP substrate, doesn't get in. This is the same substrate with an inhibitor of PGP, and it gets in. So we understand what governs tissue penetration into the tissue. So that's picking the chemistry. We can also modify our chemistry. And this is the GalNAc conjugate. So this is 3 galactose molecules. It binds the acyl glucuronide receptor on the cell surface of the hepatocyte, and that drags the molecule in. And this is now the forefront of oligo delivery, and it's providing 10 to 100-fold better targeting in the liver of the patients, and for both oligos and for Cerners as well. So that's what you do before you start your molecule process. You can also rescue compounds that are not doing so well. You can reformulate them. You can wrap them up in lots and lots of lipid and things that look like artificial viruses, and that allows you to get across cell membranes because they're fusing with membranes or they're bursting out of endosomes. As a DMPK person, as a drug developer, these are a headache because you've got 5 or 6 processes going on, 5 or 6 different components that you've got to make sure you can reproducibly construct and follow. So this, for us, is easy because it's just one component. Finally, you can change the shape of your presentation. So this is the Liquidia system, the print system, where you can actually print drug, either on its own or in a matrix, into different shapes. Now this is quite exciting because different shapes fly and flow differently. So if you're doing inhaled, you can get a different shape. It changes the exposure in that tissue. Macrophages like certain shapes to uptake. They don't like other shapes. If you coat some of these particles with antibodies, the macrophages won't touch them. So again, you can start getting cell uptake into target cells using that. Now again, this is a bit far away from where we're talking about bioreactors, but that's where we got for delivery. In GSK, we built a network to look at this. We have our oligos, and we bolt on a whole lot of different opportunities. We have chemical warheads, we've got aptamers, cell-penetrating peptides, receptor ligands, antibodies, and a big hint for this room, external collaborations where we seek other people's targeting moieties to help us there. We bolt them onto our oligos, we check for our phys props. We don't want to change those physical properties, as you said earlier, make sure we're not altering the chemistry or altering the pharmacology, and then we run them through in vitro and in vivo systems. And the idea here is the in vitro and vivo systems are the same, whatever we do at the left-hand side. So the only thing that changes in this system is the targeting moiety. And we have mice, with transgenic mice that have reporter systems in them, that we can check delivery and understand what's going on. So this is our oligos. The design was from the Giuliano paper in UNC, but it's basically a phosphorothioate oligo with targeting ligands on the end. This is an anisomide molecule, binds the sigma receptor, which is a caveolin-based receptor, internalizes very well, highly expressed in muscle and in prostate cancer. And we developed this as a system to help us with our presensor molecule for Duchenne muscular dystrophy. And at the end of the day, really, it's very easy to make because it's just like Lego. You just put the blocks together and then you can use the work. So the thing, and one take home I want to do today is say, it's all very well for drug delivery, but if you don't get the cells right, then you're wasting your time. So this is our cellular system. Myoblasts, which are muscle stem cells, can be differentiated into myotubes, and they're different. These are round and these are long and thin. In fact, if you grow these on plastic, they will pulse. Static electricity will charge them and you get pulsing. And if you want to really freak out a student, you say, go and have a look at those cells. And they go, it's all hammer, hassle, horror. But this is what we can see. If you then do cytochemistry, you can see expression of the proteins we were interested in, myosin heavy chain in green and the caveolin receptor in blue, only occur when the cells are differentiated. So if you're going to do an uptake study, make sure your cells are in the right format. And if you say, we've done HepG2 cells, so it must be going to the liver, have a think about that pretty hard. And likewise, you can then transduce them with baculovirus or other delivery systems to make sure you get them in there. And this can be done with hepatocytes, lung cells, brain cells, etc. This is just some data. This is showing we can do, using stem-loop PCR, we can follow the amount of drug in the cells and also the amount of exon skip in the cells. So that gives us a clear reading about PK/PD intracellular. So it's about ability to measure the concentration of the drug in the cells. And then we can do PD studies. This is using an exon skipper oligo that skips and makes a luciferase signal. We always do lipofectomy. And that sounds counterintuitive, but we always put a lipofectomy in there as a positive control. This shows us that if you look at the control and all the other conjugates, they're all similar in terms of their dose-response curves. That way we know we haven't knackered the pharmacology by putting this conjugate on. But when we do the naked, although we shift the concentration, you can start seeing differences in shapes and curves and shifting. And we can develop that then to find out what causes the change in potency and the change in activity and expand that. And we've managed to take our potency up to about 30-fold purely by changing the chemistry on the front end. And there's some other tricks as well in terms of backbone chemistry. But this has allowed us to take these molecules now into in vivo studies and into proof of concept studies in vitro and in vivo, ready to go into the clinic. So this is an opportunity here now to keep it going and to make a difference to our oligo portfolio. Again, 30-fold here, 30-fold less dose, 30-fold improvement in cost of goods. The next part then, just to whiz through this, we can then label the oligo. We can label our cargo to see where it goes in the cell. We can do this in vitro. And again, these are just PC3 cells, prostate cancer cells. And these are different conjugates. And you have to take my word for it because the lights aren't great here. But we get a different time course with this conjugate versus this conjugate. And there is just three chemical differences in that conjugate. Now, GSK is great at doing small molecule chemistry. So all we're doing is we're taking our skill as small molecule chemists and bolting them on the end of a macromolecule to improve that. And then we can do the same thing in vivo using fluorescent dye, real-time imaging. We can do mouse studies out to 7 days now, following the distribution of the drug around the body and seeing how we can change it with this. You can then take the tissues out, slice them, do the pathology and do your microscopic examination as well, so we can see that. And by having reporter genes in here, we can co-locate where the oligo goes, and if we switch on the luciferase or the green fluorescent protein, we can see co-location of PK/PD. Again, good for the modeling and distribution. So what have we learned within the company? Conjugation can change oligo properties. We know it's the distribution properties. You can make it go into the cell more. You can also make it more metabolically stable. Affinity and avidity are important. You don't want something that's going to bind so hard to that cell membrane that it doesn't come off again. You want something that's going to bind slightly, get taken into the cell, and then dissociate quickly. Thank you. And finally, receptor-mediated pathways can be saturated. We've seen that in vivo after a long dose. You can do that. And we had to change we had to admit we had to go wider. So I'm going to talk about the compact program now. So IMI, for those of you who aren't aware, is a European grant system. They have a pot of 1 billion euros of grant money and 1 billion euros of commitment from industry to payment in kind, of which you can then get grants against that over 7 years. We are 4 years in, and what we decided about 3 years ago, GSK went to IMI and said we need to expand our work and do delivery of macromolecules across biological barriers. Same time, Sanofi and Eckhard Lieber at Sanofi had the same idea. So IMI put us together and said, put the proposal together and then find like-minded individuals, and we did that, and we picked up Boehringer, Merck, AbbVie, Novo Nordisk and Pfizer. Now just to say that the course of this, AbbVie were original Abbott when we started this, but they've changed their name since, and that is the turnover of industry. We then recruited, over a period of about 18 months, an academic collaboration led by Enrico Mastrobatista at Utrecht, but containing several different university groups across Europe. And again, this gives us a network now to do our work with. Now, with the Compact program, and if you Google Compact, you will find our website, they have £13 million of academic grants for 5 years, and we have about 50 FTEs worth of effort going into this, full-time equivalents. We're costing GSK 2 FTEs. Now you can see that GSK is now moving its business paradigm here, where we are saying this is our return on investment. Rather than saying let's take that money and go to PhD and PhD and PhD in isolation, let's put it all in one pot, talk to our friends in Europe and get it all going together. So IMI, I've got another call coming out, I don't want to sidetrack the situation, but lots of money available outside of this room as well. The biggest challenge you can imagine is putting this together. This is our project plan. We have several different work parties working with each other. I'm very happy to take you through this later because I know I'm running out of time. But the main thing is getting, we said it can't be done. You cannot get 16 different academic groups across Europe, 7 different countries, 7 different languages to agree and work to each other. I'm sorry, it's wrong. You can. You've got to be firm and say, these are the common goals. This is what you're trying to achieve. This is your part of that jigsaw. And we're actually moving a lot further forward than we thought we would. We're coming up to 18 months in now, and we're starting to see some true results. Now, what's in it for GSK? We get access to early data. We get access to pre-competitive public access data, but it's the basic foundation of our work. And then we can build that and build on it. But we also get to be sharing that data with everybody else. I'm hearing noises. So that's the Compact strategy. As I said, to reassure you, it's possible to work with industry without them trying to take all your goodies away and keep them to themselves. And also, we can talk to other academic groups and industrial groups without feeling like we're stepping on confidentiality and IP issues. So, I'll finish off then. To deliver macromolecules, we must design the right experiments. Make sure your experiments are controlled and you understand the questions you're asking. And if you do that, it's actually very, very rewarding area to be in. We need to keep an eye on our production costs. A lot of people out there will tell you the best way to deliver oligos is to wrap them around a gold particle. Now that's great, but if you're trying to sell that down the line, it's going to make a very much more expensive product and more expensive drug, because we're trying to make medicines here, not just clever tools for in vitro analysis. You need to get all aspects of the scientific community. We hold our hand up in GSK, and my colleagues in other pharma companies the same. We cannot do this all ourselves. We need you guys, we need the academic environment to work together and work with us to do that. And that's what we want to bring here today, is our ability to network and our ability to say, let's collaborate. And GSK or Stevenage, we're very happy to host meetings, to host you guys down. My colleague Joe, who couldn't be here today, happy to host you around the pilot plants at Stevenage if you want to see industrial chemistry and industrial biotechnology in action. And we've got to continue to ask the right questions. We've got to challenge each other that these questions here are optimistic but also realistic. And if we can do that, we can end up. So to finish off 30 seconds, the now and the challenges are getting drugs into target. Okay? The soon you've already done this already, but it's the synthetic precursors. If we can get them in there, and I do have a soapbox I'll come back to when I'm allowed, that's going to be the next challenge. And finally, using membranes as templates for stereospecific construction. Because a lot of the compounds we're using need to be stereospecifically pure, and if we can't do that synthetically, we're going to have some kind of biological process in there, be it a membrane, an enzyme, a protein bound membrane, that is going to act like that template. And that's what we need to do. So I'll leave you with that and say thank you very much. My email is there. Again, I'll come back to this one if I may, because this has Joe Adams' email on there as well. Please get in touch, and we're very happy to take any questions